Lesson 11 begins something known as chi-square testing, or goodness of, there's two types of chi-square tests. There is goodness of fit testing, and then there's something we're going to do in lesson number 12. This is the symbol for chi. It's a Greek letter, and square because it's squared. That's the symbol that's going to be used for our test statistic. For this lesson, we're going to need our TI-83 calculator and also a new chi-square chart. And it should look something like this. Okay, on the top, it's going to say chi-square distribution table. It's going to give you a new table on the right-hand side. It's going to ask for area in the right tail, and they give you a bunch of areas in the right tail. We're going to figure out how to use this chart in just a little bit, but you want to download that from the website. Okay. Again, chi-square testing now is a new type of test, and there is no longer going to be standard deviation formulas for percentages and standard deviation formulas for values, and no longer a z-score, and no longer data minus mean equals over standard deviation. Those are all previous things we did before. So this is a new type of test, and to perform a goodness of fit test, you are given a distribution with 2 or more outcomes. And we want to see if this distribution is true, so we conduct our own sample and we come up with our own distribution, and we compare our distribution to what their distribution was, and we either come up with HO, the two distributions are the same, or H1, the two distributions are not the same. This is always HO and H1. They never change. HO is always same, H1 is always not the same. So each test has a significance level, alpha, just like in hypothesis testing, and that's going to be placed in the tail again. Same as hypothesis testing of the chi-square distribution, which separates the accept and rejection. So this is all the same as hypothesis testing. The remaining portion of this course deals with different statistical procedures. Since lesson number 5, we've been utilizing the bell-shaped curve for our statistical procedures, like I just mentioned. We always needed to find a mean and a standard deviation, and then we had to find a z-score. So our previous lessons covering confidence intervals, sampling distributions, hypothesis testing, and p-value all use the bell-shaped curve with a mean and a standard deviation. Goodness of fit testing is the beginning of a new statistical procedure that no longer asks for these. It uses the new variable chi-square, and like I said, we're going to need a chi-square chart, and we're going to do a few examples. Okay, we're going to jump right in. Here we go. So example number 1. Now again, we have two distributions. So the question says, the manufacturer of M&Ms claims the number of different colored candies are uniformly distributed. Now another way of saying uniformly distributed is also to say evenly distributed. Sometimes they put that in the notes also in the book. So we want to test this claim. So that means the colors are the same throughout. So you should have the same number of browns and yellows and reds and etc. So to test this claim, a randomly selected bag containing 180 M&Ms found the following distribution of colors. And we want to test to see if the color distribution is evenly distributed. All right, so here's what happens with goodness of fit testing. You always have 4 columns. First column is called the category column. And that's going to be whatever they present to you. In this case, it's going to be the colors. So we're going to write down brown, yellow, red, blue, orange, and green. Okay. The second column is called the observed column, which is capital O for short. And what you observe is actually given to you in the question. So observed values are always given to you. In this case, they're showing you that there was 22 browns and 27 yellows, 22 reds, 41 blues, 41 oranges, and 27 greens for a total of 180 M&Ms. Okay, now there's a couple hints here. I'm going to do that in just one second. For the third column, the third column is always called the expected column, which is designated a capital E. This is the one you must find. You must find these values. Okay. This particular question kind of gives you a hint. It says that uniformly distributed or evenly distributed. So what we should have expected of the 180 M&Ms is we should have had an equal distribution of them. And if you notice, there's 1, 2, 3, 4, 5, 6 columns, or 6 categories. So if we divide 180 evenly into 6, we get 30 in each category. So we should have expected 30 for each one of these. And that's going to total 180. Which leads me to my 2 hints. To find the expected, the 2 hints to make sure you don't make a mistake in a goodness of fit test. The total observed, that should be an R, must equal the total expected. That's the first hint. So whatever your totals are, they better match. And the second hint is for the expected, don't use the percentages for these values by themselves. And I'll show you what that means. Not in this problem, but the next few problems after this. Okay, so those are the 2 hints. So here's where we are. We have so far 3 of our categories. We have the categories which are the outcomes. We have the observed column and the expected column. Now we want to notice there's a difference between the observed and the expected. We should have expected an even number of colors, and we observed, not evenly, 22 browns and 27 yellows. Now, we want to know, is there enough of a difference to say that there actually was a difference, or are they close enough together to say, yeah, well, there was slight differences, but it wasn't enough of a difference to say that there actually are different. Okay. The way we do that is we find the variable, which in this case is now O minus E squared over E. Observed minus expected squared over expected. So for this one, we're going to take 22 as the observed, 30 is the expected. We're going to square that and divide by the expected 30. We're going to get a value here. And then we're going to do the same thing all the way down for each of these. Observed 27 minus 30 squared over 30. And then this is going to be 22 minus 30 squared over 30. This one's going to be 41 minus 30 squared over 30. Observed minus expected squared over expected. And observed minus expected squared over expected. We're going to find these values in our calculator. So one of 2 ways you can do this. You can either put it in just like that, left parenthesis, 22 minus 30 squared divided by 30. That's the best way to do it, just the way it looks. Okay, so this is 2.13. Then we're going to find 27 minus 30 squared divided by 30. That's 0.3. 22 minus 30 squared divided by 30. 41 minus 30 squared divided by 30. This one's the same. It's also 41. And we already did the 27 earlier. That's 0.3. Then you add all of these values up. So we're going to take 2.13, add 0.3, add 2.13, add 4.03, and another 4.03, and then finally another 0.3. We're getting back a chi-square total value of 12.92, and this is our test statistic. So like hypothesis testing, we have a value. We call it a test statistic. No longer a z-score now. It's a chi-square value. What's awesome, statistics is a language, and this tells us that we did a chi-square test. And there's only 2 types of tests for chi-square. There's a goodness of fit test that we're doing now, and then there's going to be another test in the next lesson. Those are the only 2 chi-square tests we ever do. So the fact that we use this symbol chi-square narrows down the procedures that were used for possibilities. It has to either be this one or the next one that we're going to learn next week. So this is our 12.92 test statistic. We're going to place this 12.92 in a chart. Now you don't have to memorize this because I'm going to show you in just a second. We're going to go to a chi-square table, but I want to show you right here. What I did was, this is the chi-square distribution table, and I'm matching, if you notice right here, this table here with what I want to do. And here we have a 0. This is going to be our critical value that we're going to look up in the chart. The area in the tail is going to be your significance level, which if I scroll up just for a quick second here, the question asks you for alpha to be 5%. Okay. Now if you look at the chi-square table, it says area in the right tail. Well, that's going to be the significance level we just found, which was 5%. So that's going to be 0.05. But in this case, they also asked for a degree of freedom. So this is a little different than the degree of freedom is still the same in terms of -1, but the degree of freedom now is going to be categories -1. And since we had 6 of them, we're going to say the degree of freedom is 5. So we're going to look up in our chi-square table 0.05 for alpha, and we're going to go down 1, 2, 3, 4, 5. And we get back 11.070 for our critical value. Okay, everything is except HO left of that value. Everything in the tail is reject HO, just like hypothesis testing. The reason why there's no negatives, this looks a little different than our normal bell-shaped curve or t-distribution chart, because normally there's negatives on the left and positives on the right. There's no negatives because you're actually squaring. And anytime you square something, you no longer have a negative. So there we go. Where does our 12.92 lie? It actually lies to the right of 11.07. That gets you in the tail. The tail is reject, HO. And so for this one, if I go back in the previous notes we just said a second ago, HOR, the two distributions are the same. We're going to reject that for this question, so we're going to accept H1, which is the two distributions are not the same. That's what we're going to say. Two distributions are not the same. Which means what we observed is not the same as what we should have expected, which was even distribution of colors. So we observed an uneven distribution of colors. And that's how it works. Every goodness of fit test is always 4 columns. Okay, let's do a second one. Let's see if you can do this one. Okay, so here we go. A bicycle safety organization in Arizona conducted a study of 361 randomly selected fatal bike accidents by month. The following is the last 5 months of this study. We want to test to see if fatal bike accidents are equally distributed. So that kind of gives us a hint at how we're going to set this up. Equal distributions, and we're assuming that the significance level is 0.10 or 10%. All right, so why don't you give this one a shot? This one's very similar to the first one we just did, and then you can pause and come back and see if your answer matches my answer. So the first is the category column. In this case, we could label this fatal bike accidents if we want. We're going by month: August, September, October, November, and December. The observed is what we found. We found 86 fatal bike accidents in August, 81 in September, 94 in October, 57 in November, and 43 in December. That should total, if we add all of these up, 361. We better get our total to be our expecteds also to be 361. That was hint number 1. The totals have to match. So our expecteds. This question says, is everything equally distributed? So we want an equal distribution among these 5 categories. So if we go over here and we take 361 and divide by 5 in our calculators, 361 divided by 5, there it is, we get 72.2. So if we go back over here, each one of these, if it were equally distributed, we'd get back 72.2. To see the difference between these, we do the formula O minus E squared over E. So you're going to say observed 86 minus expected squared over expected. And we do this for each one of these. Observed minus expected squared over expected. Now, you don't have to write all these down. I'm not going to test you on that. I just want to show you for good notes. And now we calculate these for each one. So 86 minus 72.2 squared divided by 72.2. Okay, so this one's 2.64 if we round. 81 minus 72.2 squared divided by 72.2, 1.07. 94 minus 72.2 squared divided by 72.2, 6.58. 57. Make sure the squared is outside the parentheses. 3.2. And finally 43 minus 72.2 squared divided by 72.2. 11.81. Okay, we add those values. So 11.81 plus 3.2 plus 6.58 plus 1.07 plus 2.64, and we get back 25.3. That is our test statistic. Okay, we're asking for a 10% significance level. Accept HO, reject HO. 0.10 or 10%. Degree of freedom is number of choices, so 1, 2, 3, 4, 5 months. Take away 1, because remember the last choice is not free. That's how we get degree of freedom. We always subtract 1. We look up 0.10 right here. And we're going to go down degree of freedom of 4. 1, 2, 3, 4. And we get 7.779. That's our critical value. And where is our 25.3? It's going to be to the right of 7.77. And that's going to land in the tail, which is the reject region. So we're going to reject HO. And that's going to tell us the two distributions are not the same. Okay. So, both of the first two questions were evenly distributed questions. Now we're going to get into a different type of question where it's not evenly distributed. I'm going to show you how to do this one. So we have two more. I'll show you this one and then we'll do another one and we should be done with the lesson. So this one, a local personnel director believes the distribution of workers leave their jobs is different than the national results. So this personnel director thinks that the reason why people leave their job locally is different than nationally. Here's the choices. You have to pick one. They either said that they left their job because there was limited advancement potential, 41% said that, lack of recognition, low salary benefits, unhappy with management, and bored don't know. Those are the choices. The personnel director sampled 200 local workers who recently left their jobs and found the following distribution. 78 people said limited advancement potential, 52 said lack of recognition, 30 said low salary or benefits, 25 said unhappy with management, and 15 said bored or don't know. So we want to test with alpha be 2.5% to see if the local workers left their jobs for the same reasons as the national distribution. All right, so that's the question. All right, so let's break it down. 4 columns. The first column is called the category column. Okay. For the category, we're going to list the options that they just showed us in the problem. Okay. I'm going to switch pens because my pens weren't working too good. And we have limited advancement, okay, lack of recognition, low salary or benefits, unhappy with management, and finally bored or don't know. Okay, the observed, this comes from your sample. Okay, so when it says that personnel director sampled 200 people, then this is what they found. 78 people said limited advancement potentials. 78 here. 52 said lack of recognition. 30 said low salary or benefits. 25 people said unhappy with management, and then 15 said bored, don't know. That should give us a total of 200. And we're going to add those up, but they also told us right here in the problem that it was 200. So for our expected, see now here's the difference now. This particular question does not say anywhere in there that these are equally distributed. In fact, these are weighted, and they're weighted based on the percentages that were given in the question. So the way we find these is we're going to multiply the probability times the total. So here's what we're going to go through. We're going to say, all right, so 41% of people said limited advancement. Well, that would be 41% of our total. In this case, that's 200. 41% as a decimal would be 0.41. And we're going to multiply that by the total of people that we sampled. So 41% of 200. Okay, that's going to give us back 82. Okay, if we take 0.41 times 200, there's 82. Lack of recognition. Up here it says lack of recognition 25%. That's 0.25. We're going to multiply that by 200 people, and that should get us back 50. 15% said low salary. 15 is 0.15. We're going to multiply that by 200. That's going to give us 30. 10% said unhappy with management. So that's going to give us back 20. And then finally we had 9%, that's 0.09, and that should give us back 18. And that total, if we take 82 plus 50 plus 30 plus 20 plus 18, we get 200, and the totals have to match. So notice this is not an equal distribution. This is a weighted distribution. 41%. If it was equal, 1, 2, 3, 4, 5, each would have 20%. That would total 100%, but it's not. 41%, 25%, so we multiply the percentage times the total, and we get back a new total of 200 with a different distribution. Okay, so now we're going to do O minus E squared over E for each of these. So observe this 78 minus the expected 82. Square that and divide by the expected 82. So this one's going to be 52 minus 50 squared over 50. 30 minus 30 squared over 30. Observed 25 minus expected 20 squared over expected 20. And then finally 15 minus 18 squared over 18. So in our calculators we're going to put in 78 minus 82 squared divided by 82. 0.20 to 2 decimals. There we go. 52 minus 50 squared divided by 50. 0.08. 30 minus 30 squared divided by 30 is going to give us 0. 25 minus 20 squared divided by 20. 1.25. And finally, 15 minus 18 squared divided by 18 gives us 0.5. If we add all those up, 0.2 plus 0.08, 0.2 plus 0.08 plus 0, and then 1.25 and 0.5. 2.03. That's our chi-square test statistic. So that shows us the difference between the observed and the expected columns. Okay. Bell-shaped. Not quite a bell-shaped curve, but it kind of looks like a bell-shaped curve. This is a chi-square distribution. It asks for a significance level of 2.5%. So 0.025. Accept HO, reject HO. Our degree of freedom in this case is categories. We have 5. And if we take away 1, that's going to give us 4. And in our chi-square table, we want to look up 0.025 and go down 4. So 0.025 is right here. 1, 2, 3, 4, we're right here. 11.143. That's our critical value. We have 2.03. That's going to lie left of the critical value, which is in the accept HO region. So we're going to say the two distributions are the same. So what we're saying is the personnel director has shown, based on his or her sample of 200 people, that locally the reason why people leave their jobs is the same as what is found nationally. Okay, so let me give you another one and see if you can do this one. All right, again, so just see if you can do this one on your own, and then you can come back and double check. But here we go. A survey conducted 5 years ago asking coffee drinkers where they enjoy their first cup of coffee in a typical day yielded 70% of people said at home, 5% said in a restaurant or other, 8% said while commuting, and 17% said at the workplace. To see if this distribution has changed, a sample of current coffee drinkers found 38 at home, 389 people at home, 27 take their first cup of coffee at a restaurant or other, 55 while commuting, and 110 at the workplace. Test using 5% for alpha, which is the significance level, to see if the results from the 5-year-old survey has changed. All right, so let's do it. Category. Where do they drink their first cup of coffee? At home, at a restaurant, commuting, or at the workplace. Observed is based again on our sample. And they sampled 389 coffee drinkers took their first cup of coffee at home, 27 in a restaurant, 55 while commuting, and 110 at the workplace. All right, we need a total. So 389 and 27 and 55 and 110. 581. So we better make sure that our total of our expected is also 581. Again, this is not an equally distributed problem because there's different percentages up there. So we're going to take the probability and we're going to multiply it by the total. So they said 70% of people are expected to have their coffee at home. 70% is 0.70. And we're going to multiply that by the total that we got back, right there, which is 581. The next one was at the restaurant, 5%. Be careful, that's 0.05 times 581. 8% said while commuting, and then 17% said at the workplace. that should total 100%, and 100% times 581 will also give us a total of 581. So we need 0.7 times 581, 406.7. 0.05 times 581 is going to give us back 29.05. 0.08 times 581, 46.48. And 0.17 times 581 is going to give us back 98.77. Okay, if we add all those up, 406.7 and 29.05 and 46.48 and 98.77. There's our 581. Now we're going to find observed minus expected squared over expected. So we're going to take 389, we're going to subtract the 406.7, we're going to square that and divide by 406.7. 0.77. 27 minus 29.05 squared divided by 29.05. 0.14. 55 minus 46.48 squared divided by 46.48. 1.56. And finally, 110 minus 98.77 squared divided by 98.77. 1.28 if we round with 2 decimals. So we're going to take 1.28, we're going to add 1.56 and 0.14 and 0.77. 3.75 is our critical value. Okay, so that's what it should look like, just like that. Okay, so we're going to draw ourselves a chi-square distribution. Accept HO, reject HO. We're asking for alpha. Again, if I scroll up, 5% is part of the question, so 0.05. The degree of freedom, there was 4 choices. We take away 1 is 3. In our chi-square table, 0.05 right here, go down 3. 1, 2, 3. 7.815. That's our critical value. We got back 3.75. That's going to lie left of the 7.815, so that lies in the accept HO region. And you're going to give me a answer. The 2 distributions are the same. Accept HO is fine, but people don't understand what you mean, so you have to actually explain it to them. So 2 distributions are the same would be what accepting HO would be for this goodness of fit test. And what we mean by that is what we should have expected to get back where people drink their first cup of coffee is the same as what we observed. Now I know we're off a little bit, but that was okay within the level of acceptance. And so we accepted the fact that we observed the same as what we should have expected to get back. So that's how you do goodness of fit testing. There's either equally distributed questions or there is weighted questions where they give you the weights in terms of a percent. And that's how you do it. So we did 2 of each. Make sure you click on the homework. Any questions, send me an email.